So we're going to continue on iterations, how to solve AX equal to B with iterations. And last time I showed you through some coding and writing some things down about how to solve AX equal to B remarkably just by setting up an iteration scheme. And that as you iterate, this thing converges to the solution. And we had a guarantee of when that would happen. The guarantee of when that would happen is when a matrix is strongly diagonal dominant. In other words, you take the diagonal element, and if its absolute value is bigger than the sum of the absolute values of all the other elements in that row, then it would, for every single row, then you'd have a diagonal dominant structure, and you can simply pick any initial guess you want, and you iterate, and it will converge to a solution. So it's a really interesting guarantee and an interesting way to solve AX equal to B, because up to this point, we've been really talking about methods that solve AX equal to B just simply by doing some kind of progressive algorithm like LU, like Gaussian elimination, or QR, or SVD. All these are sort of just reduction algorithms that allow you a way to solve AX equal to B. Well, Jacobi and Gauss-Seidel are very simple iteration schemes, and we're going to talk a little bit more about, more difficult or more advanced iteration schemes. So this is our topic: iteration methods for AX equal to B. Okay, today, in fact, I'll get around to, we're going to talk about two methods in particular. Today, the first one's going to be called the generalized method of residuals, often called GMRES, so generalized method of residuals, GMRES. And the other one's going to be conjugate gradient or biconjugate gradient methods, which often is called BCG stab, or stabilized biconjugate gradient methods. So these are going to be the two methods we're going to talk a little bit about today: GMRES, and in the next lecture after this one, is conjugate gradient methods, biconjugate gradient methods. The first thing I want to do is, why are we going after these iterative techniques? So you could always ask that question, right? Is why would I do this? Is just another way to solve AX equal to B, but why not just use LU or Gaussian elimination, because we've learned how to do those. But I want to highlight something. And the thing I want to highlight is this: progress. In 1950, I'm looking for another pen here because this one's not very dark. 1950, what we could do computationally is matrices. If you think about a matrix, which is M by M, 1950, we could solve these being about M equals 20. So not very big, right? You remember, this is the inventions of the computer. So this was very slow. All right, I'm gonna get a new pen here because that one is not to my liking. All right. So let's progress forward in time, and let's notice how well things progress. Let's jump 15 years to 65. You're about an order of magnitude bigger matrices you can solve numerically. Remember, we still don't have PCs or computers just available to anybody. 1965, it's still pretty hard to get a hold of these, and there's people that have them, but it's not widespread. So you can kind of do methods about this big, and I want to put some names down here. Forsyth and Moeller. And Cleve Moeller, he is the founder of Matlab. So he was, he actually, I believe, was working at Stanford at the time. He started thinking about numerical linear algebra, and he came up with Matlab, which is Matrix Laboratory. So at that point is when you started to see more and more access to computers by everyday researchers, okay? And Muller started developing this software package, which would allow people ease of use and the ability to do these computations in a nice way. So he was really taking modern research and putting it into a computer framework where everybody could just use it. Okay, so this is 1965. Advance another 15 year. Then you're around another magnitude up. And this is really coming into LinPack, which is a linear algebra package. And then you could start handling matrices about size 2000 by 2000. Okay, so you're starting to get bigger matrices. 1980. It's a long time ago, right? So this is like 40 years ago. And so we're starting to get bigger packages, but still pretty small for what we want to be doing. And then 1995, you get yet another order of magnitude. Now you're in the 20,000 by 20,000 range. And this is done with LAPACK, linear algebra package. And this is still sort of the state-of-the-art stuff. So a lot of the best packages always get migrated to LAPACK so that you can actually use them. Okay, so there's this migration. Now, here's the thing I want to highlight, and this is something that was highlighted by Trefethen in his book, is that if you notice over this time period, you notice we got 3 decimal places. So this is like a 10 to the 3 increase. So 3 orders of magnitude larger problems in this 45-year span. Now, what's interesting is that, well, how did hardware do? How much faster and bigger was hardware going? And on the hardware side, where you got an increase of like to 10 to the 9. So this got 10 to the 3 bigger in problems. This is 10 to the 9. So this is interesting. This got really big increase. This actually only went 3 orders of magnitude. That went 9 orders of magnitude. Now, why is that? Because if you notice, most of the packages here, or most of the methods we used here, like LU decomposition, like Gaussian elimination, like SVD or QR, these things are often, for square matrices m by m, they're size order m cubed operations, right? So we're still talking about, to compute AX equal to B solves cost you m cubed. So look at it, this went up by 10 to the 3, but since these are like m cubed, this is like 10 to the 3 to the cube power, which is 10 to the 9. So there you go. We had to get a 10 to the 9 increase in computational hardware abilities to get a 10 to the 3 increase in solving matrix sizes. So what's the problem? The problem is that this is the bottleneck right there. This is a bottleneck for solving large-scale computational problems. It costs you 10 to the 3. So the entire game around scientific computing is to figure out, is there a way to circumvent this? How do I beat this? Because as long as this is sitting there, right, if you look at our advances, every time you want to go up 1 order of magnitude, you're going to have to do 10 to the 3 orders of magnitude in your hardware development. Okay, that's a really tough thing to keep up with. Okay, so you really want to get around this 10 to the 3. So people started thinking about other ways to solve AX equal to B. And that's why we're talking about these iteration methods. Because the iteration methods are methods in which gives us at least the potential in certain cases to beat this m cubed operation counts to solve AX equal to B. Okay, so let's go ahead and talk about some of the methods out there. We already talked about Jacobi, Gauss-Seidel, but let's talk about more sophisticated methods that you'd actually use in practice. Uh-oh, that didn't erase very well. What's going on there? All right. Let me get some water on that board.
Can I ask a question?
Yes.
So you mentioned it basically goes up to 20,000 by 20,000 or 200,000 by 200. I'm just wondering.
1,000 by 20,000. That was 1995.
Okay, so is it common for the real world problem to be that size, or it actually exceedingly greater than that?
Nowadays, it's much, much bigger than that. You know, we want to solve, for instance, if you work for Boeing and you want to solve for fluid flow around design an airplane, right? And start numerically solving for this, you know, for the fluid flow around an airplane, you might want matrices that are billions by billions. Let me say it this way. There's no matrix you can make that's big enough that people would go, that's too big. What everybody wants is they want bigger, faster. If you tell people I can solve trillion by trillion matrices, tomorrow people will show up to you and say, here's my problem that I need a trillion by trillion matrix. You know, people are doing now simulations of galaxies, right? This is massive simulation. And the only thing limiting them is they can only do certain size simulations limited by the largest supercomputers in the world. And that's their hard limit. That's the biggest they can do with memory and solutions and solution techniques. So there's no upper limit is the way I think about it. You build it, people show up with problems. And they want to do it fast.
So all the algorithms you use today are basically limited to one computer. We never thought about, like, for example,
people do all kinds of methods where they can also, they do whatever, multi-threading, right? So you spread out the computation across GPUs or CPUs, and then multi-processors. Yeah, you can do lots of algorithms that take advantage of this too.
So in that sense, there should be no limit at all, right? Because you can theoretically,
theoretically, yeah, you can, you know, but then there's limits of hardware communication, right? So oftentimes when you solve these, even if you can break it apart, so iterative methods are really nice for parallelizing, except for you still have to make them talk to each other at some point. All the local computations still have to be integrated into the final solution.
I see. So that becomes a bottleneck eventually. Got it. Thank you.
Yeah, and so we're going to so what we're talking about with iterative methods is exactly all these things, is how do we get around this issue of this M cubed? In other words, any of the really large scale problems, nobody is doing Gaussian elimination. Nobody. You're always doing something else that's faster. Nobody can afford, even in today's problems, to say, let me go do this big fluid flow example. You're not going to do Gaussian elimination on it. You're going to do something much more sophisticated. And so this gets us into the iterative techniques, and let's talk about it in a more formal way. I'm going to introduce to you the idea of what's called a Krylov subspace. So I'm given a matrix A and some vector B. And what I want to do is think about what a Krylov subspace is. And this is a kappa n. I'll tell you what this is in a minute. The Krylov subspace, its span here, or the subspace of this, is given by the following set of vectors that span this subspace. So the vector B, A times B, A squared B, all the way up to A to the n minus 1 times B. So I'm looking at the subspace that this forms. Okay? So notice what I'm doing is A squared. So this is, in some sense, this is an iteration structure, right? I hit B with A, hit it again, hit it again, hit it again, n minus 1 times. And then what I'm looking for is these set of vectors. This is the Krylov subspace. How I'm going to take advantage of them. But the other thing you know about this Krylov subspace, since I have these n directions, right? First direction, second direction, all the way to n minus 1. I started with n equals 0, so there's n of them total. I could, in fact, span this with a set of vectors that are orthonormal. Okay, and these are a subset of the m-dimensional space. Notice I'm only going to n dimensions. So out of this m-dimensional space, I define an n-dimensional subspace in this fashion, which, by the way, I could say, well, if this is an n-dimensional subspace, I could come up with instead with n orthogonal vectors. By the way, how would I do that? Well, I would define, I'm going to do this with a QR decomposition. Remember, the QR takes a set of vectors that aren't necessarily orthogonal, and then I can move them to a coordinate system in which I have, instead of n these directions, I get n orthogonal directions. So we're going to make use of QR here in thinking about how do I want to take advantage of these Krylov subspaces. Okay? So that's the space I want to work in. And so we're going to start defining some things. In particular, what I want to do is define the Krylov matrix. So this is kappa, this is K. This is going to be a matrix, and the matrix I make here is B, AB, A squared B, all the way to A1 minus 1B. There it is. So this matrix is going to be really important for us as we start to look for solutions to AX equal to B using iterative techniques. And the method we're going to use is what's called this generalized method of residuals, okay, GMRES. And it's going to exploit this kind of structure in this kind of space. But by the way, a matrix such as this, I could in fact do a QR decomposition. So this thing here can be decomposed into Q of n, R of n. Okay, so notice that n is telling me how many of the columns I want, right? And remember that A is an m by m matrix, and this is m by n. And n is the number of iterations I do in this Krylov subspace. And notice that this subspace, I can in fact move me over by Gram-Schmidt orthogonalization to the QR so that I get n orthonormal directions times some R of n, which is the mapping from this space to that space. Okay? So what this is actually telling you, what is it actually telling us? Remember that what we do in Gram-Schmidt. Gram-Schmidt says, I have all these vectors. They're not orthogonal. How do I basically make an orthonormal basis? They're not only not orthogonal, but they're not, they're not normalized. So what I do, the first row of Q of n is you just take this vector B and you normalize it. That's how we did it before. We just say, pick the vector B, normalize it. That is Q1. How do I get Q2? Q2, I take the second vector and I project out the direction that's orthogonal. So I project out the direction that's already along B, and I say, what's the direction that's orthogonal to B, or Q1 now? And that's what, remember, we worked with those orthogonal projectors, household of triangularization. That whole Gram-Schmidt business comes right back here to say, okay, go in my second vector, Q2, I pick this vector, make it so that it's orthogonal to my first vector, that's Q2, normalized. And then I pick the third vector. I make this as my initial guess, but now make it orthogonal to the two previous, normalized, and so forth. That's how I get this Q of n. Okay? So this Krylov subspace is sitting there, and it turns out what it's going to allow us to do, this Krylov subspace, is going to allow us to construct a recursion relationship, and I'll show you that in a little bit, which is going to allow us a very fast way to get a search algorithm for the best solution to find this AX equal to B solution through an iterative procedure. Okay, so Krylov subspaces, you see them everywhere. Every time you're going to talk about iterations, iterative solves for x equals to b, you're almost always going to talk about Krylov subspaces. They show up everywhere. Okay? All right. So, with that defined, let's move on. I'm not sure why my board is being so terrible today. It's pretty bad. A lot of black showing up here. I'm going to do one more wipe down. Usually it's not this bad, especially with a fresh pen. Okay. Hopefully you're closer there now. Okay, so now we're going to do is turn our attention to this generalized method of residuals. All right. What is it and how do we operate this thing? Remember, what we want to do, solve x equal to b. That's almost always what we want to do, right? All these decompositions, this whole quarter, all we've talked about is different algorithms. And they all come back to solving this, right? And the decompositions actually tell us a lot more, like an eigenvector decomposition, eigenvalue decomposition, the SVD. They tell us things about the matrix A, like the spectrum, what the singular values are, tell us important directions, unitary matrices that tell us interesting things. But really, at the end of the day, they all come back to solving x equal to b, usually. Okay? And remember that A itself is some m by m, and B here, m by 1. Now, let's suppose this actually has a solution. Let's call it x star. So x star is equal to A inverse B. So that's the truth. That's the ground truth. The question is, how do I compute this? Because you wouldn't actually take the inverse of this thing. It's super expensive. Remember, the entire goal here is not to say, can I get a solution? It's how fast can I get a solution? Hopefully everybody understands that. The whole game of a lot of this linear algebra is not, can I get a solution? It's always about how fast can you do it, right? Computational speed. Remember, I showed you that chart. It took 10 to the 9 increase in hardware to get us 10 to the 3 increase in matrix size. This is a really tough growth rate if we have to get 10 to the 9 every time on the hardware just for a 10 to the 3 increase. So we're trying to beat that. What we'd love to have is if you increased your hardware by 10 to the 9, your matrices went up by 10 to the 9. That'd be fantastic, right? But we're trying to figure out methods that just get us the solution and do it faster. This is about the slowest way you could possibly solve this, is to compute that inverse. Okay, so GMRES. Generalized method of residuals. So what it is a method that's pretty simple. All we're going to do is start an iterative procedure where at every iteration, we're going to minimize the residual. What do I mean by that? I want A of x equal to B, or ax minus b to be 0. But when I give it a guess x of n, this isn't satisfied. So the residual, it's called R of n, is equal to b minus a of x of n. Okay? So there you go. This is the residual. If you got the right solution, if this is x star, then x minus b is 0, and the residual is 0. In the meantime, remember how these iteration procedures work. You give it a guess. You start with x0, which gets you to x1, which gets you to x2. And what you would like to do is figure out, how do I determine an update rule for the x of n so that this thing will iterate and converge to the solution x star. Okay. So the entire idea here is, by the way, the x of n is going to live in the space and the Krylov subspace. Okay, so that's, I get to pick a vector out of here, out of this Krylov subspace. So this is where the Krylov subspace comes in. This is my subspace for representing each pick. And what I want to do is basically put each x of n, and I want to pick x of n through a least square fit. Okay? Least square fit, and remember, I'm going to start off with x0, and I'm going to get x1. So in other words, it's going to have to live in the first Krylov subspace, K1. And then when I go to 2, it can live in the space. Remember the Krylov subspace looked like? It was spanned by B, AB, A squared B, so forth. So I am constrained. This x of n has to live. Each time I iterate, I get to broaden my Krylov subspace. So first it only can live in here, then in here, then in here. Okay? So that's the idea behind this. So this is going to be some n-dimensional space trying to represent, this thing is m by m, but this thing here is a small space, you know, it only spans an n-dimensional space out of that m-dimensional space. So that's the main idea. That's it. So then the question really comes down to is, all right, so given that this vector x of n lives in that Krylov subspace, how do I determine the x of n at each iteration that minimizes this at each step? And the idea is that if I start off with an x of 0, I get a number, and I go to x1, x2, and this should get smaller and smaller and smaller, and the residual should just start to decrease. And then you're going to stop this when you get close enough to the real solution. Okay, so that's the main idea behind GMRES. All right, let me get the next paper here. All right, so let's start setting this up so we can solve. Oh, man. This is a bad day for board. Okay, well, let's leave it like that. All right, so we're going to solve ax equals b. And remember, I'm trying to play around with this x. And so I want to ask the question, what happens when I multiply that matrix A against the Krylov matrix? Okay, the Krylov matrix, so in other words, A acting on K of n. Remember, K of n is B, AB, A squared B. So this here becomes AB, A squared B, A to the NB. Okay? And so really what I want to do is think about like, well, my vector x is going to live in this Krylov subspace, which is a linear combination of those vectors B, A, B all the way through here. And so one way to think about this is what I'd really like to do then is to minimize, in other words, the vector x, one way to think about it is x of n is going to be a linear combination. I'm going to live in this subspace K of n. So x of n is going to be a linear combination of those Krylov subspace vectors, which are B, AB, A squared B. So I'm just going to do a linear combination, and C is going to tell me how much of each column I need to represent x of n. The question is, how do I pick C? I want to pick C so that it minimizes the residual. Okay? So another way to think about it is this AK of n here. What I really want to do is say A, K of n, C. Remember, K of n, C is like my x. So that's A x of n minus B. And I want to minimize this with respect to the vector C. That's a least square fit right there. Okay? And what C is doing is saying, I am a linear, if I'm going to represent this x of n, I'm going to pick C, which is a linear combination on Krylov subspace, Krylov subvectors, times A. I have B, I have A, I have K. So I have everything except for C. I want to determine those C's, those projections onto the K of n's, the columns of K of n, such that this quantity here, this L2 norm, is minimized. Okay, that's the high level idea of generalized method of residuals. That's it. You just at each step minimize the residual. That's the residual. Okay. Now we could work directly in this Krylov matrix K of n. But what's the problem with working with K of n directly? K of n is a bunch of columns, right? Let me just draw it back here. B, A, B, all the way to A of n minus 1b. None of these are necessarily orthogonal to each other, right? They're not even normalized. So they're just a set of vectors. You can clearly do a linear combination of them, but we've started to learn in this class, hopefully, that isn't it more advantageous to work with orthonormal vectors? This is the power of the SVD. It gives you U and V, which are unitary transformations. This was also the power of the QR decomposition. It gave you a unitary transformation times an upper triangular. And we use those to great effect because those are very easy to manipulate. And we want to do the same thing here. What I mean by that is, instead of working directly with this Krylov matrix, we know that this thing here has a QR decomposition. And so instead of using these as basis elements, why not just use the QR? Why not use these Q of n's? They're orthonormal. This is a unitary transformation. It is much better to work with that matrix than the K of n. But this Q of n comes directly from the Krylov subspace. Okay, so this is a better representation of the Krylov subspace, but nonetheless, it's still coming from that. Okay, so instead of solving this problem, what we know is we can say, well, another way to do it is this here, which is my x of n. I could instead say x of n is equal to, instead of projecting C times Q of n as a linear combination, I could instead say, well, why work with that basis when I could work with the Q of n's? And y is now what I try to determine instead of C. Remember, C is just the loadings onto which one of these, the linear combination of these columns, whereas y now is same idea, but now onto an orthonormal basis, which is much easier to work with. So really, at the end of the day, what I would do is instead of using this x of n, you trade it out for Q of n y. Okay? So this is a nice representation of that Krylov subspace. All right, there's a lot of pieces to this, by the way, and I'm going to also make this comment. I'm only doing a very superficial scratching the surface of iterative methods. If you look at Trefethen's book, there's a whole lot more there. Also, there's entire books on iterative techniques, one by Anne Greenbaum, that is probably the best in the field. It's all about just iterative solvers for linear systems, and that's a whole field in itself. Okay, so we're just talking about some very high-level concepts here because we have so much to talk about in the course, and so we're not going to get into a lot of depth here. But I'm going to sort of sketch out for you some of the important things here, and then if you want, and you get very interested in this stuff, there's a lot more out there to follow up on.
I have a quick question.
Yes.
So does the fact R is missing here affect which set of columns you're selecting?
The fact that R is missing?
So
Sorry, I'm not sure if I understand the question.
So instead of saying X being KC, now you're using QY, right?
Yeah.
So basically you're saying X is QY without considering R at all.
Yeah, I don't even care about R. All I care about are these orthonormal vectors. That's it. I just want to go from working in that coordinate system. So in other words, this here spans that subspace, and that's all I care about. I don't really care how I got there. Once I get them, I use them.
Okay.
Yeah. All right. So I'm going to do a lot of name dropping today. Just one of those types of lectures. But sometimes that's how it goes. So the next name to drop is Arnold, or actually Arnoldi. Arnoldi iterations. I was talking about Arnold Schwarzenegger, but these are like Arnoldi Schwarzenegger. Anyway, this is like the powerful method for doing iterations, and it turns out it underlies a lot of the fundamental ideas of these iteration techniques. Arnoldi iterations. Okay, so now we're going to come back to some ideas that we already learned before about matrices, and we were doing this with eigenvalue, eigenvector algorithms, which is transforming the matrix and then using the iterative procedure to find the eigenvalues and eigenvectors. So in particular, we can write a matrix A in self-similar form with the following transformation. Q is unitary, and H is Hermitian. So this is a full self-similar transformation into a complete orthonormal set of vectors, and this is in, sorry, not Hermitian. Sorry, Hessenberg. So you can put this in Hessenberg form. In fact, that is one of the ways, the first tricks you do for doing eigenvalue, eigenvector decompositions. If you remember what we talked about, some of the algorithms there, the idea was to recursively first put it in Hessenberg form, and once you have it in there, then finish off your eigenvalues by doing iterations, okay? Here, we just have this form which tells us, okay, I know I can do this decomposition. And this is where we're going to make a connection to this idea of when I do a part, as I start to do this decomposition. This is a full decomposition. And if this matrix A is massive, I don't want to do a full decomposition. What I'd really like to do is start doing this decomposition, stop wherever I want. Okay? And so I want to go n iterations in. And what does that look like? Well, so first of all, I can rewrite this by multiplying on the right-hand side by Q as AQ equals QH, okay? And what I really want to look at is how would I get the first n columns of that Q? Okay? Now, it turns out if you do a little bit of linear algebra, I won't do it here, you find this interesting relationship. A acting on Q of n is equal to Q of n plus 1 Hn. So all these are partial decomposition. So this, I'm not doing a full decomposition. What I'm looking at is just the first n columns. And here's the important thing. You find when you do the first n columns, there is a recursion relationship between Q of n to Q of n plus 1 because this thing is Hessenberg. So we can work this all out, by the way. And in fact, what this tells you is that A acting on Q of n is equal to H1n. In fact, let me write down the Hessenberg matrix. H is equal to H11, H12, H1n. And remember, it's diagonal with one of the below diagonal not being 0, H21. And everything else here is 0. But because it has this form, it creates a recursion relationship between the Q of n to Q of n plus 1, which is H1n Q of 1 plus all the way to Hn and Q of n plus Hn plus 1, 1 n plus 1 Q of n plus 1. And this is a really important recursion formula. It's the basis of these Arnoldi iterations. In other words, once I have the Q of n, I can get Q of n plus 1. Once I have the Q of n plus 1, I can go get the Q of n plus 2. Once I get Q of n plus 3, I can go get the Q of n plus 3. I have a connection formula that tells me how my n connects to the n plus 1. Okay? So this is, in some sense, a different version of Gram-Schmidt, right? Because I start off with a certain number of directions. Remember, Gram-Schmidt, you start with Q1, which then allows you to get Q2. Once you have Q1, Q2, it allows you to get to Q3. Once you have Q1, 2, Q3, you get Q4. Same kind of idea here. Once I'm just building it recursively. And this is the recursion formula that you have from this diagonalization here, which is a self-similarity transformation to the Hessenberg. And remember, if you look back at those lectures on eigenvalues and eigenvectors, we talked about how could you do decompositions in a principled way to put any matrix in a Hessenberg form, and then from that Hessenberg form, then you can finish it off with iterations. So this is the main idea behind Arnoldi, is I have now a recursion relationship that allows me to just iterate from Q of n to get Q of n plus 1. Okay? So we have this formula here. This is an important one. Okay? And we have A of Q of n. Now remember, let me erase here what we had previously. How do we bring Arnoldi in then to this GMRES? Well, if you remember what we wrote down with GMRES, we were trying to minimize the residuals, and that was minimize this, Q of n, y minus b. Well, A of Q of n is here, is actually Q of n plus 1 H of n. So when I come back to here, then I'm saying, well, I'm going to minimize this over y, which is equal to minimize over y. This A of n, Q of n is now Q of n plus 1. Now this Hessenberg, nth Hessenberg form, y minus b. Now, turns out y and b are both in the column space of Qn plus 1. And so what I could do for both sides is multiply by Qn plus 1 star. In other words, because it's a unitary transformation, I can simply take the inverse of it to basically get the following. Okay? And remember, what I'm trying to solve for is this here, this y. So I want to minimize the y's. I have this matrix now. I can compute everything. And this is an upper Hessenberg form. So it already is in the spot, and it's in a situation where it sets me up very nicely for doing, in fact, a least square fit. So there's a lot of steps I'm skipping here because I just want to get to the punchline, and so that you at least have the main idea. But this is the idea. Remember that iteration techniques, and I said this previously with eigenvalues. Iteration first make a transformation into some favorable variable setup like Hessenberg form, and then do iteration. We were talking about that in the context of eigenvalues and eigenvectors, but notice I just did it here in the context of solving Ax equal to b. Use that Hessenberg form, and now I've set myself up to do the iteration from here. Okay? All right. The only other thing I want to point out here is that this guy here because now it's in the nth plus first direction, this is equal to the magnitude of B times E1 vector, which is 1, 0, 0, 0. So this thing here just results in, and I know I'm skipping a lot of algebra, but that's just the way it's going to go for today. Boom, minimize that, respect to Y. So this is your generalized method of residual algorithm. So let's talk about how we do it in practice as an algorithm. Your first direction is the B. This is just like Gram-Schmidt. Remember that I'm working with this Krylov subspace. Remember what the Krylov subspace was. Krylov subspace, Krylov vector for B, A, B, so forth, all the way to A of n minus 1B. How did we do QR on this? We picked the first direction and normalized it. That's Q1. Okay. Now what do I do? Well, what I got to do is now go get all the other vectors and start this process n times. So for n equals 1, 2, 3, so forth. First, I do Arnoldi, which is this guy right here. Okay. Nth step of the Arnoldi. Solve this. Okay. Sorry. The Arnoldi is what I erased. It was the Arnoldi is what's going to give you, sorry, I erased it. It was that recursion formula. And once you have that recursion formula for getting the Q of n plus 1, right? So that's the thing you want to get is you get your next Q from that recursion relationship that I showed you, which was the Arnoldi formula, right? Of A acting on Q of n, which was related to the Q of n plus 1. Then once you have that, then you do this minimization over Y, H, Y minus B, U1. And then your X of n is equal to Q of ny. So you solve that Y, your next X of n is you just project onto those orthogonal directions. Repeat. That's it. So when you come back up here, you connect it to the next direction, Q of n plus 1. Now you can solve this. Now I'll go here, Q of n plus 2, and you just recurse. So that's generalized method of residuals. So you see it's kind of fancy, but it's, I mean, if you kind of spend some time with this building up to this GMRES lecture, there's like 3 or 4 lectures in Trefethen, and I compressed it down to 1. Sorry about that, but all the details are there. And my feeling was I wanted to cover other materials instead of just getting bogged down with this. And what I'm going to do in the next lecture is I'm going to actually show you this other algorithm. So biconjugate gradient stabilized method. So it's just an algorithmic structure, conjugate gradient descent. And I'll show you that. And then what we'll do is actually show you in Matlab how they work. Matlab has all this stuff programmed in. This algorithm's in there. And then so you can solve a lot of these AX equal D problems by just one line of code. And here's the line of code. Ready? X equals GMRES A, B. Simple as that.